Now we have the penultimate section on mechanics, which is work, energy and power. We will do work and energy to start with. Outline what is meant by work, sometimes called work done. The work done is the force times the distance through which that force acts. An example. We have an object here. We need to find the work done in moving that object when we make it move. We apply a force, let's say 2 newtons. We make it move. The distance it moves is 3 meters. The work done is the force times distance. 2 times by 3 gives 6. 6 joules of energy is the work done in moving an object which needs 2 newtons to make it move through 3 meters. What if the movement is not in the direction of the force? It must be in the direction of the force. Otherwise, we need to find the component of that force that is acting in the direction that it moves. For example, we have a force of 10 newtons acting at 45 degrees. The work done in making it move 2 meters is not 2 times by 10, which is 20 joules, because it's only the horizontal component of the 10 newtons that is actually doing the work. So it's going to be the work done is force times distance times by the cosine of the angle between them. When the cosine is 1, in other words, when it's 0 degrees, then it's force times distance. What about here? The force is acting at right angles to the movement of the object. If it moves 2 meters that way, this force is doing no work. This force is not doing anything to make it move 2 meters. And this angle, by the way, is going to be 90 degrees. So it's force times distance, 2 times by 10 times by the cosine of 90 degrees, which is 0. So no, this force does not do any work in moving that 2 meters. There must be another force that is doing that. None. Determine the work done by a non-constant force by interpreting a force displacement graph. Okay, we know this. The work done is force times distance times by cosine theta, if that's necessary. If we have the force times by the distance, the force is constant during that distance. So, force times distance, well, the geometry of this shape gives us the area. So the area of a force distance graph will be the work done. So the work done is a total area under a force distance graph. Now what happens if force is not constant? We can take the average force, or we can find out what the area of the graph will be. We take an example, stretching a spring. You know that when you stretch a spring, to start with, the force is small. The more you stretch the spring, the more the spring pulls back, so the more force you need to apply. And this is what the graph looks like. It's force times distance, but the final force is not the force that it is applied for the whole stretching of the spring. When the spring is not stretched, there is no force. But nevertheless, we need to find the area under this graph, which is the area of a triangle. Half base times by height. This is base times by height. This is half base times by height. So in other words, we can either take half the force and take that average that way, or, to be more specific, we take the area under this graph. So the work done is half the force times by the distance, or the extension. Next is kinetic energy. Kinetic means moving. So the kinetic is the movement energy that a body has. Its kinetic energy is half mv squared. So notice there has to be a velocity. If the velocity is 0, the kinetic energy. If the velocity is 0, the kinetic energy must be 0. This is K stands for kinetic energy, m is the mass of the object, v is the velocity of the object, or speed. This is kinetic energy expressed in another way, which is very useful to use. You know that kinetic energy is half mv squared. If you multiply it by m divided by m, which is the same as multiplying by 1, the kinetic energy will be the same, and this term will be the same. But if we multiply by m, we have m times by m divided by m. So it's going to be m squared v squared divided by 2m. Now, you know that mv, mass times velocity, is equal to the momentum. And sometimes we write momentum as p. So the kinetic energy is p squared over 2m. This is a very useful form of this equation. Kinetic energy is equal to p squared over 2m. Because if you don't know the velocity, but you do know the momentum, this equation is more useful. You can always find the kinetic energy from the momentum, finding out what the velocity is, and then finding out the kinetic energy. But that's an extra step. If you're given the velocity, you use this equation. If you're given the momentum, you use this equation. Outline what is meant by a change in potential or gravitational potential energy. The change in potential energy or gravitational potential energy is the mass times the g, the acceleration due to gravity, times by the change in height. So it's basically, it goes from one height to another height. The distance that it moves, the vertical change in height, times by g times by m, will give you the change in potential energy. The greater the change in height, the greater the potential energy. Also, the greater the mass, the greater the change in potential energy. So this is the mass times by the gravity, the gravitational constant, which is g, or the acceleration due to gravity, or the gravitational field strength that we will meet in a later topic, times by the change in height. And this is the same equation as this work done against gravity. Is force times by distance. The force is the weight, which is mg, times by distance, which is the change in height. So the best way to remember this is delta PE or PE is equal to mgh. That's the easiest way to remember it. State the principle of the conservation of energy. The total energy in a system is always constant unless some energy is given to the system or taken away. Another way of saying the total energy before an interaction is equal to the total energy afterwards. Any energy that appears to be lost is converted to another less useful form of energy. For example, heat to the surroundings or sound to the surroundings. Here's an example. We have, this is the total energy, this is time. If you throw a ball, it starts off with a lot of potential energy. When you drop the ball, it starts off with a lot of potential energy, which goes to 0. When you drop it, the kinetic energy is 0. But then, as it loses potential energy, that potential energy is changed into kinetic energy. So it starts off with 0 kinetic energy, and at the end, when the potential energy is 0, the kinetic energy is a maximum. In fact, it's equal to what the potential energy was in the first instance. So that all the potential energy is converted into kinetic energy. No energy is lost. The second point is that when you add the potential energy and the kinetic energy, at all points they should add up to the same value. I did this deliberately, where they cross here, exactly the midpoint here, the midpoint of energy. So you add them together, you will always end up with the same total. This is the principle of the conservation of energy, unless energy is lost to the surroundings. Here we have an energy conversion. A 500-gram ball is thrown upwards with a velocity of 5 meters per second. Find the kinetic energy. Find what will the kinetic energy be when it reaches its highest point? Well, all the kinetic energy it has to start with all gets changed into potential energy. So what will the gravitational potential energy be at that point? It will be whatever the kinetic energy was to start with. How high will it reach? Well, you can figure that one out. What if the ball has twice the mass? Do the same calculation, but not with a 500-gram ball, but with a 1 kilogram ball. List different forms of energy and describe examples of the transformation of energy from one to another. You should be able to do this quite easily. Give examples of kinetic energy turning into other forms of energy.